Welcome back. Maybe you have noticed that we pushed everything 15 minutes, and I hope we'll keep that schedule. And yeah, without further ado, we have the first presentation, at least I know of, which will be partly remote. And yeah, I will see how that goes. And welcome.
Thank you very much. I hope it goes well. So we'll talk about certificate transparency today and what it takes to support this critical internet infrastructure. This presentation is brought to you by two industry leaders, Let's Encrypt and myself, of course. And a few things about me. I live in Zurich. I was working at Google in security. And then a few months ago, with 250 of my Swiss colleagues and 12,000 people around the world, I was laid off. So now I'm unemployed. I have a lot of free time to do talks like this. I'm very interested in networking. So I have an autonomous system with over 1,500 BGP neighbors and presence in 3 Swiss internet exchanges. So it's going really well. I know this is a networking event, but we're going to talk about a few layers above layer 3. And we'll start with HTTP, which is how we all access the web. And more specifically about its secure version, HTTPS. So HTTPS ensures that when you visit a website, you're talking to the right server, and nobody can read or modify the data that is being exchanged with this server. So here, over the past decade, we have come a really long way in terms of HTTPS adoption. Here are some statistics from Mozilla for Firefox, which show that around 80% of the pages loaded with Firefox are done securely over HTTPS. And in some countries, like the United States, this is over 90%. Google has similar statistics. They report 93 to 99% of the page loads across major platforms, and Linux, of course, at 81%. And in terms of time spent, things are even better. 95 to 99% of the user's time is spent on a secure website, at least in terms of network-level security. This is all possible because of TLS. TLS is the protocol that gives HTTPS its security properties. It sits between HTTP and the rest of the network stack, and it tries to protect everything above it. And it's being used in other places as well, like email with SMTP and IMAP, IRC. It has so many use cases. It's the easiest way to add end-to-end encryption in an application. And TLS, in order to work well, it requires certificates. So every time you connect to a website, you have to have a certificate to authenticate this connection. And obviously, our computers and our laptops cannot have like one certificate for every website. This wouldn't be practical. So we have this sort of hierarchy here, which is called the PKI. So we can store a few hundred certificates that are trusted in our computers, and then we can form paths from them to the certificates used by individual websites. And for the web, for web browsing, this is called the Web PKI. And you may have heard a similar term, which is the RPKI. And I'm going to go over a few differences here. In the RPKI world, once an hour or something like that, your software downloads a list of all the active certificates out there, and then it processes them, it verifies them, it checks the data, and then it sends it to your router so you can drop prefixes or do whatever you want with it. In the Web PKI, it is different. When you connect to a website, you're presented with a certificate, and then when you connect again, you have to get the certificate again. And it may be a different one. This is the biggest difference that we're going to concern ourselves with today. And just to get an idea of the size of the Web PKI, it's a bit larger than RPKI. There are over 4.8 billion certificates that we know of, and over 500 million of these certificates are currently active and unexpired. And every hour we have over 250,000 new certificates being added, which is faster than the rate at which they expire. And some statistics, currently Let's Encrypt, the largest CA, controls 50% of the certificates, or actually issues 50% of the certificates. And then it's followed by a quarter, which is DigiCert plus Amazon Web Services, and then some smaller CAs like Sectigo or Komodo, if you've heard of them like that, and Google and Microsoft. And in terms of the total certificates we know of, Let's Encrypt is basically at the 3/4 of all certificates ever issued that we are aware of, basically. And it's followed by Sectigo and then DigiCert, Amazon, Google, and Microsoft. So it is a significantly larger PKI that we have to secure. And it's very important because every time a user uses a browser to connect to the internet, to connect to a website, they rely on that, and we have to get it right. However, it doesn't always go well, either because some CAs can be hacked, or they may be malicious, or they may be misconfiguring some server or mistyping something. They may cause significant damage. Because all of these CAs are basically equally trusted by computers, even if you have DigiCert on your website, someone presents a DigiNotar certificate, it would be trusted. So we have to make sure that these tens of organizations out there, they do their job well and they don't risk users. DigiNotar here, for example, they issued certificates for CIA, Google, and Microsoft, and they used this to attack internet users out there. They presented these malicious certificates, and they tried to get users' data by decrypting it. So this is not good, obviously. We can't protect the users if this is happening every day. And this is why certificate transparency was created. Basically, we have these certificate transparency logs, which are data buckets. And in these data buckets, we upload all the certificates that have ever been issued. So if a CA issues a new certificate for a domain name, then they have to include this into 2 or 3 of these data buckets out there, so everyone can look at it and verify that. If I have a website, I can look at these data buckets, I can look for my domain name, and if there's a certificate I don't know about, I can take action. Or researchers can just look at all the certificates and maybe find weaknesses in some cryptographic keys, or find some certificates that don't look right, and they can investigate further. So we have these collections of certificates. And you may ask, like, if someone wants to hack Microsoft users, why would they publish the certificate they're going to use to achieve that? And the reason is that operating systems like Apple's iOS and macOS, as well as Google Chrome, they will not connect to a website unless this certificate is actually published in these data buckets. They will not trust this connection, they will not exchange any data until this certificate is public for everyone to see. Mozilla Firefox, for example, does not do this, but they still benefit from certificate transparency. They still benefit from researchers looking at these certificates, identifying bad ones, and then taking action, even if it doesn't happen at the connection stage. So certificate transparency is good for everyone using the web out there. And here are 6 companies right now that operate these data buckets. It is these 6 companies that offer their resources to make these publicly available buckets possible. And we're very lucky today because from one of them, from Let's Encrypt, we have Phil to tell us more about what it takes to operate one of these city logs. So Phil, can you tell us more about that? You are live.
Slide shared. Good afternoon, everybody. My name is Phil Porada. By day, I'm a mild-mannered software engineer at Let's Encrypt, helping to build and maintain important parts of the Web PKI. And by night, I'm super dad. What that means is I keep the cartoons running for my kids. I've been at Let's Encrypt for just over 6 years, and it's the best job I ever had. So what is Let's Encrypt? Let's Encrypt is a nonprofit certificate authority that provides TLS certificates to over 325 million websites actively. We're supported primarily through corporate and non-governmental organization sponsorship. And to date, Let's Encrypt has issued almost 45 million certificates for the Swiss ccTLD.ch. And of those 45 million certificates, about 2.9 million are currently in active use. So this particular talk is going to be a rehashing of some previous blog posts that we've written about certificate transparency, how we've built and operated logs. These slides will be available afterwards, so you'll have all these links. And along with that, there's going to be some more stories, because you can't operate a reliable log without first failing all over the place. So certificate transparency involves logs, and there's also this concept of shards, and it can get a little bit confusing. So each Let's Encrypt certificate transparency log is made up of individual temporal log shards, which are named after a period of time. Each shard is technically a separate CT log, sharing a family name, such as oak, which is a production log, or sapling, which is a testing log. So it can make sense to conceptualize each shard as belonging to a single log. Every new shard that we create overlaps with the previous shard for a short period of time while we monitor performance and ensure correctness. This overlap is a protection against the possibility of any significant downtime as our certificate authority switches shards. Too much downtime can lead to a log becoming unqualified, and other certificate authorities around the world would be unable to use it. There was actually an incident that we had with our own certificate authority software, Boulder, several years ago, where we were unable to submit our certificates to enough logs due to a misconfiguration on our part. When a log rollover happens, when one shard ends and another shard begins, the certificate authority wasn't able to submit certificates to the new log, and we started receiving errors. We had about 7 of us gathered around a hotel lobby table investigating, sending out communications, and deploying a fix. And since about 2018, this has been happening seamlessly in the background for us now. So how does a CT log benefit a certificate authority? As a certificate authority who also operates some of these logs, operating a log helps us take control of our destiny, meaning our uptime. Apple and Google Chrome require all new domain validated certificates to be submitted to 2 separate distinct logs. And by running our own CT log, we can fulfill at least half of that requirement for our organization. For OV, organization validated, and EV, extended validation certificates, the number of required distinct CT logs increases. And given that Let's Encrypt often issues more than 3 million certificates per day, we needed to set out to design a CT log infrastructure that could handle not only our high volume, but also the volume of other publicly trusted certificate authorities. And the screenshot that I have here is from Firefox, showing an arbitrary website with 2 signed certificate timestamps embedded in it. These are a cryptographically verified receipt of sorts that we submitted our certificate into the Let's Encrypt Oak log and a Cloudflare Nimbus log. So we had several failed architectures. This diagram on the screen is no longer in use. We set out to deploy our own CT log back in early 2017. we did an initial feasibility test in Amazon Web Services with an RDS database and EC2 instances. We used SaltStack to orchestrate much of the setup and learned how the pieces of this software fit together. And then we destroyed that test because it was just for testing. And then in 2018, we began in earnest. We would eventually attempt to submit this architecture and the log behind it for an inclusion request to Apple and Google Chrome to get it trusted. We did cost-benefit analysis, sizing analysis, arranged a deal with a physical server host, and then encountered numerous problems leading from unavailability of physical server hardware, constant network issues between data centers. It got so unreliable at the time that we implemented a Berg BGP router between each of our data center POPs. And that worked well for a while. And ultimately, we got rid of this architecture and moved over to Amazon Web Services again. So here on the screen, I've got our current functioning architecture, and lots of these diagrams are pulled from blog posts that I mentioned earlier. So the infrastructure has changed slightly since our initial deployment of this architecture in 2019, and we've learned a lot about what to do and not to do and gained some experience. The image on the left shows the original architecture diagram I made, and while the picture on the right conceptually illustrates how we split apart various shards into separate databases. Primarily, the software we run for our CT log is made by Google. It's comprised of two specific projects called Certificate Transparency Go and Trillion. Amazon handles some aspects of the backing database for us with their RDS service, but we're still responsible for all the performance tuning, migrations, and monitoring. Certificate Transparency Go provides the personality, which is the Golang implementation of an RFC called 6962, and it handles communication with the Merkle tree, the cryptographic bits that are handled and implemented by the Trillion project. The Merkle tree itself is stored in a database. In our case, we use MariaDB. And aside from the various diagrams, we run everything in Kubernetes as containers. Other open source software that we use are Nginx as a reverse proxy and etcd for elections within the Trillion software. Additionally, for monitoring, we run Prometheus to scrape metrics from underlying hosts, the databases, and applications. And then we send alerts to our SRE team with Alert Manager. The Oak 2023 log shard is currently still accepting certificates issued by Let's Encrypt and therefore services a high volume of requests. Here in this picture is a historic 90 days of Merkle tree growth. There's always a baseline of roughly 30 to 40 requests per second with various high spikes leading well past 400 requests per second. And with an active CT log shard, that log is always going to be performing many, many operations. The majority of traffic that we receive is actually not from certificate authorities, but from researchers, monitors, and CT log mirrors who want to copy all of the data that we have so it's stored in more than one place. When someone requests a set of data from our log, they can get back a maximum of 256 certificates per network request to limit the amount of time that our database spends retrieving that data. Downloading an entire log from the very first entry to the last is our most significant demand of disk I/O on the database, and ultimately where problems arise. So a fun incident regarding that was back in August of 2020, we performed a routine set of application upgrades and noticed a log line above that, oh, we ran some MySQL or MariaDB commands out of order. Thinking it was a bug, we rolled back the software updates that we did. And then we asked the Trillion team for help. Digging into what this specific warning was, we thought, oh, it's probably unrelated to the application upgrade, but let's just go be sure. So our thought that it was a bug was incorrect, but it lined up just perfectly with an application upgrade. Turns out this was a performance problem caused by an abusive client pulling data from every oak shard that we had all at once. This person was launching multiple short-lived VMs to bypass our Nginx rate limits, and they generated traffic in excess of 600 HTTP GET requests per second. And our database at the time definitely couldn't handle that. And then typically we could service about 110 to 120 GET requests per second, which was mostly from just other researchers. And this person was blowing way past the rate limits. So we had to implement a few quick mitigations to get back into a functional state. The first was we set up a nastygram in Nginx for their specific user agent, and we severely rate limited them. The second mitigation was to implement a set of global rate limits per RFC 6962 endpoints. Certificate authorities will primarily send post requests rather than GET requests to a log. So certificate authorities wouldn't be affected by this. The intended purpose was to limit the damage that an abusive researcher or client could do to our log. And the final mitigation was to configure a maximum number of MariaDB connections to limit saturating the database with connections. In the event that a Trillion process exceeds its configured database connection limit, the MariaDB driver would wait for an available connection before dropping an error to a user. There's a human cost and a compute cost to running a CT log. Typically, Let's Encrypt spends about 3 months of 1 to 2 engineers' time per year to do routine application upgrades, maintenance, things of that nature. For compute, we basically just use commodity hardware. We use Amazon EC2 instances. They're nothing particularly special. And all you need is enough storage and RAM on the compute nodes to run these various applications. But the database, that's going to be the area of biggest cost. Horizontal scaling is still the best solution that we have to keep our CT logs running. The faster the storage is on your database's hard drives, the better log performance you'll receive when data is read from disk. Additionally, we no longer use one gigantic database, as our blog posts talk about. We use many smaller databases, and we have several CT logs per year to limit the amount of active data in a database. And so on this last slide, there's just a bunch of takeaways. Nothing, and it's probably difficult to read on the screen in front of you, but this will be available in the slides after the presentation. That's all I have, so I'm going to pass it back to Antonis. Thank you very much, and I hope you all have a good afternoon.
Yeah, thank you, Phil. We have a few more slides. So let me run quickly through them so we can be on time. So let's go back to these 6 companies that are currently operating these city logs. You may notice a few problems with them. The first one is that they are just 6 companies. So if you need a minimum of 3 of them at any time, that means that if one goes down, there is significant trouble for the entire ecosystem. We cannot add certificates there, we cannot issue new certificates, and we cannot protect the users that rely on these certificates. And this is bad. We also have a few plans of how we want to grow the ecosystem, and with the current limitations, it makes it a little bit difficult. The other thing that you may notice is that there is some lack of diversity in this group. And by many metrics. So that's not very good either. So what we need actually to solve this problem and to continue to be able to provide this service for everyone is that we need more city logs. We have to get more city logs. We have to get a 7th company there at least, if not an 8th or a 9th or a 10th. And this is where you come in. Perhaps you want to run your own city log. You want to be the 7th company in that slide. So every time I run this presentation again, your logo is up there. But what does it take to do this? Apple and Google have some guidelines and some requirements, but basically what happens is you set up the software and then you wait a month or two, however long it takes for you to be satisfied that you can run this reliably. And then Google is doing some metrics at the same time, and they test whether you configured it correctly, whether the uptime was good, things like that. And if everyone is happy, then you become the 7th company in that slide. Or organization, doesn't have to be a company. And there is a lot of support doing this. The community mailing list out there is very helpful. You can get troubleshooting tips. You can just talk to people, see if there is any bug or anything like that. You will receive help. And the software that Google wrote has a Slack channel, and they provide actually a lot of great support as well. They're very friendly, nice people that are going to help you succeed as well. But specifically for SwiNOG members, there is this email address. And if you are even considering running a city log, if you want to figure out whether that's the right thing for you, if you want to discuss technical details or implementations or anything like that, just send an email there, or how to convince your manager. Just send an email there, and I will receive it, and I will either try to help you myself, or I will put you in touch with the right people in the ecosystem to make sure that, first of all, this is the right thing for you. You're not just taking some work that you are going to regret in a few months or years. And second of all, that this is a successful attempt and everything goes well. And there are people that volunteer from Let's Encrypt that we saw and from other city log operators that are there to provide the know-how to make it better for everyone. So that's all I had for today. You need to run a city log. That's what you need to walk out with. And if you're a managed provider and you have managed databases or load balancers, prove to us that they are good by running a city log. Just show us how good your databases are, and also help run this critical part of internet infrastructure while you do it. And you also get to be on my slides. So thank you.
Thank you very much. Any questions?
Yes. Okay. Yes.
Hey, I don't know if Phil can still hear me, but anyway, I will ask a question. He mentioned that he used the CT RFC 6962, which was replaced by the RFC 9162 with a version 2.0 of CT.
Yes.
So my question is regarding that: do they have to change something in the architecture regarding this new draft for implementing that?
So that is a good question. I can try to answer it because you can no longer hear Phil. But the thing is that some people came up with a version 2 of CT, and the only thing they fixed was that they did it differently. They liked it more that way. I mean, there are some technical advantages there, but it hasn't been really adopted. So it's not something that you need to worry about. The version 1 is still the currently active version that everyone is running and using, all the browsers, all the CAs.
All right, many thanks.
Thank you for providing that interesting insight. I was a bit worried, to be honest, when I saw that slide about where the data is stored. So not only the companies are all run by US government, or mostly run US based, but also they're storing data on AWS, and obviously Google would be running stuff on Google. Are there any attempts to diversify that in terms of not only using hyperscalers and also making sure that maybe if several companies join the initiative that they don't store everything on AWS?
So there is no requirement for diversity, but some of these companies there are running on their own infrastructure. And one of them is actually having servers in the UK. It's just that it is still a US company. So this is possible. You can do it, like with enough SSDs in some hardware, you can host it anywhere. It's just that in AWS, you know, it is easier for most people, especially if they can afford to pay the bill. Okay.
No more questions? Okay, then thank you very much.